Welcome back. In this segment, we will study a series of formulae, most of which you need to know. The first one is the sum for I equals 1 to n of k. Now, k is a constant that does not depend on I. Therefore, what you're adding here is k to itself n times. So the answer to that is n times k, because there are n terms in the summation. The second formula is the sum of the k times a sub I. A sub I is the term in some sequence, and k again is a constant that does not depend on I. Therefore, you can take k out of the summation to get k times the sum of the a sub i's. The third formula has to do with a summation over terms or expressions that involve the addition of two terms in two different sequences. Well, because addition is commutative, we can reorder these additions. We can group all of the a sub i's together and all of the b sub i's together. So not surprisingly, this sum is equal to the sum of two sums, the sum of the a sub i's and the sum of the b sub i's, over the same indices, of course. Now, this is probably the sum that you will see the most often. We've seen it before. We'll see it again. It's the sum of the first n positive integers from 1 up to n. Well, you need to know this formula. We'll prove it later in the course. It's equal to the last number in the sum times its successor divided by 2. Now, let's compute the sum of the first n terms in an arithmetic progression where a is the initial term and d is the common difference. We can actually come up with a closed form formula for this summation using only these four formulae. So first we have the sum of two terms, so we could separate this overall sum into the addition of two separate sums. The a's on one side and then the d times I on the other side. Now notice, d is a constant, so when we're going to do the sum of the di's, d is going to come out according to this formula, and then we're going to have the sum of the i's left over. Now, this quantity here, according to the first formula, is just n times a, and this quantity here, according to the fourth formula, is what? It's the last term, n minus 1, times its successor, n, divided by 2. Notice we're starting at 0, which means it doesn't count. So it's like we're starting at 1 all the way to n minus 1. So we're going to have d times n minus 1 times n over 2. And then the way this formula is usually presented, if you look it up, is to factor out the n over 2. And this is what's left over. So this is a closed form formula to compute the sum of the first n terms in an arithmetic progression. Now, let's move on to the next formula here. The sum for I equals 1 to n of I squared. Now, this one you don't really have to remember, but it's an extension of this one where we're summing the squares instead of the integers directly. We basically get this term multiplied by an extra term to get n times n plus 1 times 2n plus 1 divided by 6. Again, this is the least important one so far. Just wanted to put it up there in case you need it later. How about this one, which is pretty useful? The sum for I equals 0 to n of 2 power I. So here we have the powers of 2, right? 2 power 0 plus 2 power 1 all the way up to 2 power n. Well, it turns out the answer is this. Now let me show you. You don't have to memorize this. You can actually figure it out. So what is 2 power 0? Well, that's 1 in binary, right? And then we add 2 power 1. Well, that's 2. So in binary, 1 plus 2 is 3, which is written like this. And then 2 power 2 is 4. So in binary, we add 4, which is a leading 1 here. Notice what happens is in this sum, we're adding all of the powers of 2 starting at 0 all the way up to n. So in other words, say n is equal to 3, then we would have a binary number with all ones, especially n plus 1, 1, because you have 2 power 0 here, 2 power 1, 2 power 2, 2 power 3. So this is the number 15, right, written in binary, and this is the sum of the first 4 powers of 2. Now let's say I'm going to add 1 to this number. What do we get? Well, we're going to get 16, which is 1 followed by 4 0. Notice 16 is 2 power 4, so it's 2 to the power n, which was the last power in the sum, plus 1. So now what I'm going to do is I'm going to subtract 1 from both sides of the equality, and what you get is that this sum that we're computing is equal to 2 power n plus 1 minus 1, and that's the formula. Again, you could prove that formally, but intuitively, hopefully it makes sense. Now, one way to compute this sum that starts at m is to compute the bigger sum that starts at 1, and then to subtract the extra terms that we included here, all the ones from 1 to m minus 1. So here is an example where this formula is useful. Notice we have a formula here to compute the sum of all the consecutive integers up to n, but we have to start at 1 to use this formula. Here we can't use it since we're starting at 57. So we can use this formula here to rewrite it as the sum for I equals 1 to 123 minus the extra terms we just added from 1 to 56. And now we can use this formula here, which tells us that this is 123 times 124 divided by 2, and similarly this term is 56 times 57 divided by 2. So we subtract the 2, plug the numbers in our calculator, and that's a pretty easy way to get this sum right here. Now these two sums are also equal. That's easy to check. This is the sum of all the integers from 0 to n, 0 plus 1 plus 2 plus 3 plus dot 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 plus n minus 1 plus n. Whereas when the index I goes from 0 to n, this is the sum n plus n minus 1 dot 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 plus 2 plus 1 plus 0. So it's exactly the same sum, just in reverse order. And we obtain that by replacing I by n minus I in the summation. Now here is a formula for a phenomenon that we observed earlier. Starting from this sum, we can rewrite it as a slightly different sum, where the index of summation here, I, is shifted downward by k. So you go from I to I minus k, where k is any integer constant. And to make sure you get the same value in the end, you just shift the values of I upward by k. So you go from m to m plus k, and from n to n plus k. These two sums are equal by index shifting, as we discussed on a previous example. Now, remember up here we computed the value of the sum of the first n terms in an arithmetic progression. So how about this sum, which is the sum of the first n terms in a geometric progression? Remember that a is the initial term and r is the common ratio. Well, here is the formula. It's equal to a times 1 minus r to the power n divided by 1 minus r, which of course does not work when r is equal to 1, since we cannot divide by 0. So what happens when r is equal to 1? Well, these terms becomes just a, and according to this formula, the sum of a n times is just n times a. So make sure you get comfortable with all of these formulas, and make sure you're able to use them when you need them later on.